Ready to go?
I think so.
Good. Okay, share the screen. Get scared. Scary. Let's see how things are arranged in the right way. And I only can see a few of you now. Can we make this longer? No. What do you guys see right now? My hand?
Yes, for the hand.
Yes, your screen.
And my screen here?
Yes, with a paper
And
mouse.
that one?
Yes.
That's
Yeah,
Excel.
your
Good.
deck.
I want to undo that again. Oh, dang. How do I do that? Yeah, I have screen problems too, so I'm gonna be safe today. I originally wanted breakout rooms and so on, but I think we're gonna be safe, and maybe it's a little bit shorter session that way. But let me first introduce myself. I'm Matthias Kawski. I've been with the DNA Math Circles project since the beginning almost. So Charmaine, as you see here, who was in the film, I'm in touch with her, and she just yesterday sent me email and said she's very busy with her PhD now, but she 9 years after the film started and the project started, she is close to her PhD in biomedical engineering. So I'm very proud, and so we are still in touch. So to find me, if you Google me, Kawski comes in right at the beginning. And if you Yahoo me, you get Kawasaki, but that's actually a good way to remember my name, because you don't want lawnmowers and tractors or motorcycles, so it's a few A's missing. And you can always find me going to ASU. My private page is in here, and I have all my links in here. So there's tons of stuff, in particular the math circles at ASU. Now, what I did today is I'm gonna give you, I'm gonna work with these ones and these links, and I'm gonna put them to the Navajo Math Circles website where we are on the schedule. So I'm gonna make sure that the links appear here. But right now, oh, sorry, that's a wrong one. Right now, if you want to see my Excel worksheet, all of these ones are available in here. So it's only on my schedule. So my homepage and schedule and appointments, and where did we go in here? So we're gonna work the light bulbs problem. And so I have this one on paper. That's gonna be easier. But before we get to this one, I have a few comments about the previous games. When I was a kid, this one was one of my favorite games. So this one is very similar to what Dave just did. Dave played one of the takeaway games, but this one is just flipping black to white and white to black. It's just a real fantastic game. So Othello is the modern name. I knew it as Reversi, and I've played endless nights playing this one. So you try to make it all black, I try to make it all white, and it's a real fun game. So Reversi or Othello is a real cool one. Then I had a few comments about, that was my Jamboard, let's see, about our congressional districts. And Dave just was talking about gerrymandering in Kansas. This one is what our congressional map looks like in Arizona. And I think those ones don't look like they are really thin and skinny things. What do you think? So all the Diné Nation and the Hopi together, but also the Apache and Gila River. So that's one reason they curve around in here. This one is not cut up into little teeny tiny strips, just as to dilute something. So when I looked at this one, I just said, actually, this one is pretty good. So inside the city, there are some funny areas in there, but otherwise, I think this one is a pretty decent map and not like Kansas. Dave, what do you think? Compared to Kansas, this good or bad?
This looks better. I mean, it's better than I had mentioned. When what I said was not correct. I had not looked recently. I had a different impression.
So the one which is next is, these ones are the counties. So the counties are different from
That's
the congressional maps. But usually when we look at the numbers coming up, they are list tabulated by county. And what I always said, this one is kind of strange that the delineation is cut up into 2 strips and then the rest to the left. And I always thought, I don't quite understand that the county seats are all the way in the south. So this one is Springerville, St. John's, Holbrook, Show Low. And I had the feeling that this one would, if these ones were congressional maps, then I would really think about dilution and making it 2 red and 3 blue or something like that. But these ones are the county maps, and the county maps are different from the congressional maps. And for the county maps, what really matters is what the population is. So here are again the 2 strips in here, and we see
I'm
these
in
ones.
math training. Nisha is down with a headache, so.
Which one? I did not catch that. Can you repeat? Am I still on?
Yeah, you're still on. It sounded like somebody is leaving down with a headache. And we will record this and put videos on so it can be watched.
Okay, no problem. So I'm going to finish this one in a moment. So basically, these ones are the 2 long strips, and they have a population of 100 and a little bit less than 100,000. Congressional districts are about 700,000, and so Arizona has 9 congressional districts of 750,000 each. So congressional districts need a much, much larger number. In Arizona, the smallest counties are really, really tiny. So Greenlee has hardly any people in there. It's wonderful backpacking wilderness in there, but there are no people, only wolf. And then at the other end, we have 4.5 million in Maricopa. So there's a huge discrepancy. And I think looking at this map in here, I'm pretty proud of Arizona compared to when I look at maps from South Carolina and the way Dave described Kansas. So I don't know what's going on there. So I actually pasted those links into the chat earlier, so they are easy to find. Let's see, is there anything else? No, this one is for later on. Okay, then let's go and start with, let's go on this link in here. And we're gonna go on the left side. It should be this. Good. So basically, I wanna play a game with you and do some simple arithmetic. And this one is known as the backpack or locker problem in high schools. But the way I have it written up here, it says, thanks to the Stan Wagon at McAllister and for the extension of the famous locker problem. So if you go on the web and search for locker problem, there's always one version which was in the math contests, very popular. But that one really had only one problem, one line. And what we have in here is we have 24 different versions of that. And we're gonna go through half of them or so. And then instead of taking lockers in a high school and closing the locker, opening the locker, closing the locker, opening the locker, I think the idea of light bulbs is really nice. So this version and this write-up comes from the Math Circle's Julia Robinson Math Festival, and it is written by Josh Zucker. Is he the author? It says directed. So Josh is at, what is it called? Oh, no, I forgot the name.
Josh wrote many of these. Last I heard, he was at Proof School, but I'm not sure where he is. I need to catch up with him. Part of problem solving.
Is he still in Alpine in San Diego?
I don't know. I need to look him up.
But anyhow, this one will be posted later on. And so what we have is, let's read this one together. And I tell the story. So I have a long row of light bulbs. So think of this one as a long hallway, and there's light bulbs, and each of them has one of those hanging switches, and you can walk by and turn it on or turn it off, turn it on or turn it off, turn it on or turn it off. And so in this write-up, they have 1,000. I think 1,000 is too many. And I asked, and I hope that I distributed these ones earlier so that you can play with pencil and paper. My original idea was that we use the annotate thing in here, and I take stamps, and then I can turn, stamp, good. And then I can turn things on, on, and we can do this one collectively. And but I think I'm gonna work a little bit faster instead of using the stamps, which we can do collectively. I'm gonna play with my with pencil and paper here on the side, so we can do it both ways. And then I have a little Excel sheet written so that we can check our results and test them. Good. So the usual story is these ones are all lockers in a high school, and you open them, close them, open them, close them. I think the light bulbs are nicer. Good. And at the end of the hallway, so this one is at the left, and there's a lot of students standing. Oh, forget about this column here. And they are numbered 1, 2, 3, 4, 5, 6. So it's very important that they remember their numbers, because when you count off, like I'm number 1, 2, 3, 4, 5, and at the end I say all the twos walk forward, then they all say, oh, I forgot what my number was. So you know that problem, but they all remember which one it is. And the story is, the easiest one is that we are having everybody walk the line, and what they do is the first one turns on every light bulb, switches every light bulb. And here comes the same problem that Dave had a moment ago. And what did you have? The zeros were white and the black ones were 1. Is that right, Dave? I think you had the black and white ones switched. I always would do it the opposite way.
For me, black was on and white was off. So mine were not like they were reversed.
So that is my issue too, because I don't want to start with black paper and then make white light bulbs in there. So I think we have green and white as we switch them around. So the first person goes through and turns every one of the dark light bulbs on. So at the end of the line, all of the lights are on. Are you with me? I don't see anybody anymore. Everybody tuned out. That's scary.
I see.
Good. So if you have your own copy, that's fine. And otherwise, I'm gonna leave the screen on here on the left-hand side. So if you wanna play with annotate and stamp, and you go along, sorry. You're welcome to work on my screen. Is that possible? Can you all actually put stamps in there too? Can you help me filling out this line? Can you use your annotate and go to stamps? I don't see anybody joining me. Ed.
I am not sure how to do that.
So on my
That's fine.
on my control panel for Zoom, on the bottom it says share and chat and participants. I have a button, oh, there it is, with annotate. Good. So the first row is, and if you hit annotate, then I get a bar. For me, it's on the top. It says mouse, text, select, stamp. And then we have played games in the past where different players have different stamps. So Ed and Casey, that's not allowed what you're doing, because we are only in the first row. So this one's gonna, no, drawings. Oh, I did not want to do that. I only wanted to erase a few ones. Okay, so the ones on the bottom should not be on. So the first one has turned all the light bulbs on. Can you remove the, let's see, can I clear, save, undo, eraser? Good. I'm gonna erase yours, erase the second row because we are not there yet. Good. So the first student has turned all of the lights on. Now, the second student goes in and flips every light switch, every other light switch. And the way we start this one counting is to make it a little bit easier. It doesn't start with the first one, but it counts off 1, 2, and then takes the second. The first one is on, so it doesn't do anything to the first one, so that stays on. The second one, since it's number 2, it turns it off. The third one we leave on. The fourth one, he turns it off. The sixth one stays on. The sixth and the sixth one gets flipped on. Oh, darn. So I'm gonna leave this one up to you to continue this line, and I'm gonna do the same thing on my screen, on my paper here on the side. And let's see it. So you're working on that one collectively. There's one difference which I would like to have changed, but talk about that in a moment. So I have every other one switched. So since they were all on, they become white, and white means black. Good. Fake means truth, and truth means fake, and green is blue, and red is, okay, all of this stuff. Now comes the third student, and the third student changes the switch, pulls the switch for every third light. So it doesn't do anything to the first one. It keeps the second one the same and switches the third one, so this one becomes white. It doesn't do anything to this one, not to this one, and turns this one on. Don't change it. Don't change it. Change. Don't change it. Don't change it. Change. Don't change. Don't change. Change. Don't change. Don't change. Change. Are you with me? So we are looking at this always at, we're counting off don't switch, don't switch, don't switch. And I hope that I get this pattern right. So it's, which one did I just switch? I switched this one. I don't do anything to this one. I don't do anything to this one, and I switch this one, so this one changes from green to white. I don't do anything to this one. I don't do anything to this one, but I switch this one. You get the pattern? Hello?
Yes, sir, we're following.
Good. So you saw I have some trouble with that because I say don't, and then at the same time my fingers have to actually color it. So this one is a fairly hard thing for my mind-finger coordination, because I want to, whenever I say do, then I want to paint it. No, that's not the job. I want to just copy it and then switch every third one. Now the fourth student goes through and does the same thing, only that it switches every fourth one. Now to make it a little bit easier, what I have is I actually have a little program in here, and what's the best way of doing it? I'm gonna do it right now with my Excel spreadsheet. So what I have is, no more drawing right now, please. I clear everything. So, And I want to switch it to Excel, so I have to get out of the annotate. Yeah, I think this one is fine. So what we said is the first person goes through and turns everything over, so everything gets turned on. And what I do is I select all the light bulbs and cancel. And I just say, no, this one was correct. And I'll tell you in a moment how I'm doing that. And I just do Control right. And so all of them are turned on. Fair? Now the second student comes in there, and I'm gonna copy down the formula. So all that I do is Control D in my worksheet, and it copies my formula. We're gonna talk about the formula in a moment. That comes afterwards. But this one then, let's see if this one looks like what I did by hand. Does this one look right? At the beginning, they were all on, no, all off. The first students turned them all on. The second students take every second one and flips it, but flipping it means turning every other one off. Agree? Is that good?
Yes, sir.
Good. Now comes the third one. This one was the one which was a little bit trickier. So it is Control D. And then I say we're going to the right. So what is it gonna do to the first few? Does this one look right? So the first one is kept, the second one is kept, the third one is switched. Keep, keep, switch. Keep, keep. What's the next one?
Switch.
Switch. Get it? So my computer is better than my fingers in here. So we want to play this one with many different versions. And so this one should be the pattern. And if I look at my board here, I think I did not quite get that one right. Can you see these ones? So I have these 3s and 3s, they look right, but at the beginning I definitely had some mistakes. Good. Now let's see if we keep doing this one and we have the first 40 students do the whole thing the same way. Like the pattern?
Wow, that's nice.
Good, so I did this one for the first time here. So basically the idea is, if you're doing this one with students, you can do this one at all ages clearly, but the tricky part with flipping them is that when I'm coloring, it is that I have to paint something at the place where I don't want to do anything. And I think the way Dave had it, it is easier by saying this one is a coin, which is heads up or tails up. Good, and then it is, then you have a row of coins and you just flip every third one. So in that case, it's easier than coloring things. So taking physical things like coins, or let's take this one in here. I have a medical bottle tops and I take them upside down. And so going along the line is nicer. Compared to previous games which I've done, this one is not as collaborative as other ones because we couldn't start the fourth row until we are done with the third row. Agree? Good. Now let's take a look at what happens at the end. Which lights are left on at the end of the day? So this one is left on. Which number is that? This one is column. Say it out loud. This one is column.
Column
1. Agree?
column 1, yeah.
One.
And then the one.
Actually, let's do this one in here. Just as a reminder, I copy the names in here. Can you see which rows are have their lights on?
3 and 2.
No, those are, I want to think of
1,
1,
1, 3, 5.
No, I want to count the white ones.
Arrows.
1,
1,
149.
47,
4,
4, 8,
8,
16,
9,
24,
15, 25,
36,
36, 41 to 48.
41 to 48, and then 50 to 60.
Yeah, I'm looking at the white ones. Oh, sorry, this one didn't quite work. And I want to take the color off. So is this one a surprise? What do you see in those numbers?
How is 49 marked red when the last one is black?
What's the next red one? What's the next red number gonna be? What's the next red number? Once more, 1, 4, 9, 16, 25, 36, 49,
63?
64.
yeah. So in order to
64.
do this one,
It's
I need
one
a few
squared.
more. So I need to have a few more students
Then
walk through
81.
here. And I can do this one by copying my formula down further over the worksheet down right. And what you see, the next row where the light is on at the end of the day is, can you see this column here?
Yep, 64,
64, and the next one is gonna be
81.
81. So what are those numbers?
Those are n squared.
Yeah, they are all the complete squares or perfect squares. Agree?
Yeah.
So the first question then is, why is that so? So all of the other numbers get turned off. All of the other lights at the end of the day, they are off. They get black, black, black. And the only ones which stay on are the perfect numbers. So don't look at the red numbers in here. Just let's look at the black numbers in here. Any idea what is happening? Let me fill this sheet all the way up. So I don't have 1,000, I only have 100. Oh, that's why I screwed something up. Best idea is to close it, don't save, and start with the same thing again. Open. Good. So I'm starting with the same sheet. And what happened was when I filled this one to the right, I went a little bit too far. It is up to 100. And then on the right-hand side, there's something else happening, which are side calculations. And I'm gonna go down 100 rows too. So this one is the pattern which we wanna have. So why are the complete squares left over? Ooh, what is this one? Oh, I see. Why are the prime numbers all on at the end of the day? Give me a reasonable sized prime number so that we can do some thinking. Maya, I can't see your eyes. That hurts. Let's see. Can I make this one larger? I want to see more of your faces. Oh, it doesn't allow me to. Oh, now I have more of you on the screen. That's better. So I'm just on my screen. I think you cannot see this one, but I'm looking at all the participants in there, and I felt so lonely when I only saw 3 of them. So I make this one a little bit larger. Now I can see you. Good. Somebody has the camera on. Thank you, Leandra. Who else has the camera on? Let's go to the second page. Good. Let's move this one out to the side. Okay. So let me think of a typical number, and let's say that the prime number is 17. So we are in the first row. What happens at the beginning? It is dark. It was a 0. Then 1 comes through. Does 1 turn it over? Does 1 turn over number 17? The 17th light bulb? What did the first student do? The first student did
Um,
All of them.
all of them. Agree? So in particular, since the first student turns all of them on, this one gets turned on, and then whatever, there are lots of 1s in there. What does the second student do?
I can see the center of the paper, Matthias.
Good. So the second student doesn't do anything to the first one. So this one stays on, but it makes this one a second, this one a second, this one a second. So on the 2nd, 4th, 6th, and 8th, and so on, this one turns them off. Will it turn off number 17?
The number 17?
2.
Or
It changes the 2, it changes the 4, it changes the 6. Does it change the 8? So
Eight.
this one flips all the even numbers. Agree?
Yeah.
But it will
Before
keep the
17.
17 in there because 17 is not even. Agree?
Okay.
Good.
Yeah.
Now the third student comes in, and it doesn't change the first one, so that stays. It doesn't change the second one, but it changes the third one, and so on. Which one does it change? It changes the third one. It changes the
sixth one,
6th one.
the
It
ninth,
changes the
the 9th.
9th one. Will it change the 17th one?
No,
Because it goes 3, 6, 12, 15,
the factor of
18.
3.
Good.
Goes to
12,
factor of 3.
15, 18. What happens to 17? 17 stays on.
Yes, the
Agree?
same. Yeah.
Now the 4th student comes in, and the 4th student flips the 4th one, the 8th one, the 12th one again, the 16th one, the 20th one. What happens to 17?
It stays the same.
It
Still
stays on. Does number 5 flip the 17th?
No.
Does number 6 change?
No.
Does it ever change?
It does in 17th.
So when 17 comes along, it makes the 1 into a 0. Agree?
Yep.
I flipped this one all around again. Where's 17?
17 is right here. Yep.
What happened to my numbers in here? Oh, this one is a prime number.
17 is the first part.
So what happens to prime numbers? So if I have a prime number, it got flipped at 1 and at 17. Agree?
Yeah. Prime numbers only flip on their factor.
Yeah. So 17 is black at the end of the day. Give me another prime number.
23.
Which one?
23.
23.
Yeah. It's the same.
So once more, 23. So who switches 23?
The 23rd student.
So at the beginning it was turned off. The first one turns it back on. Agree?
Yep.
And then it stays on all the way until
22
22, and 23
is where it turns off.
turns it off. And then afterwards, the numbers are all bigger because they don't change anything. So student number 33 leaves all the first 32 alone and then only starts working at 33. Agree? So we don't have to look at what the later ones do. So the prime numbers are all the prime numbers off at the end of the day?
Yeah.
Why? Because 41 gets once turned on, and then at the end of the day, 41 turns it off again. Agree?
Yep.
Good, so there's two of them. And let's see if I have these ones right, and I don't. Yikes.
29.
No, this one should be, there's something wrong in my worksheet, not the way I wanted it. Okay, so this one tells us that the prime numbers are all off. What happens to other numbers? So some numbers get turned off, turned on, turned off, turned on again. How many times do they get turned off and on? So let's take a real good number. I think this one is one of the more famous numbers. They're not perfect, but actually, Dave, you have a name for that? 30 is a special number. What was the name by number theory people? If it's the sum of its divisors itself. Okay, so let's look at 30. Who are the people who are gonna flip 30?
Perfect. Yeah.
30, we have 2.
Yeah, so 30 gets flipped by 1 and by
1 second.
2, agree?
Yep. By 3rd.
3, who else?
5.
And
6.
and
10.
and
15.
15 and
30.
30, agree? So at the end of the day, is it on or off?
On, off, on, off, on, off, on, off.
Agree?
Yep.
So this one is a total of 8. And 8 is an even number. So that means it is
Or off.
off, on, off, on, off, on, even number. We are back to off.
Off.
Agree?
Yep.
Good. I'm not gonna give this one away right away. Let's take another number, which is where we have to do some work. I'm just mean. Let's take 48. What is 48 at the end of the day? Who turns this one off? The
Even
first
so,
one
it
turns
turns off.
everyone on. Good. The second one changes all the even numbers. So
Yeah.
this one is an even number, so it is off again. So
Off.
it gets changed by 2. Then
number
it
3.
gets changed by 3.
Yeah.
What are the other? What's the next
4.
one? Which 4 changes it?
6. 8. 12. 16. And we have 4, 24, and 48.
How many are they?
1, 2,
1,
3,
2, 3, 4,
7,
5, 6,
10.
7, 8, 9, 10. Agree?
Yep.
So
Even
10 students will switch it 10 times in a row. So when is the color, when is it off? If this one is an even number, it's switched an even number of times. Agree?
Yes.
So if we look at this picture in here on this worksheet, you see lots of black ones, and the only ones which were not switched off at the end of the day were the complete squares, or perfect squares. Oh, need some white paper. Where did my white paper go? Oh. So let's do one on the side which is similar, and And then hopefully we can do some theory, and then we have fun with other people doing this one. What about 36?
36 is even and consonant.
So
consonant.
tell me very quickly who switches it. The first one switches everything.
1,
The
2,
second one switches all the even ones.
yep, 3,
3. What are the others?
6,
4,
4, 6, and 9, and
6,
so on. 9,
9.
12,
What then?
12, and 18,
And
36. 36.
good. So this one is a perfect square. And how many do we have?
3, 4, 6, 8, 9.
9. So this one is
Off.
on at
Odd.
the end of the day. Agree? So the perfect squares are on and the other ones were off. And this one were off. So how come that the perfect squares have an odd number of students which flip it, and the other numbers which are not perfect squares don't have an odd number? They have always an even number. What does it mean to be even?
Because even numbers are divisible by 2,
Yeah.
but
You understand?
the perfect.
Let's think of this one. We're making pairs in the classroom now. So I want you all to pair up. And if I look at my screen on the bottom, it says we have 47 participants. How many pairs does that make?
47.
47.
That is 40, 61, 23, and 1 excess.
1 is left over. Agree?
Yeah.
Good. So when I think of even numbers, that there's an even number of things, I want to pair them up. And when there's an odd number, there's always something left over when I pair them up.
Yeah, because there's a square number.
Yeah, why is it? Why do square numbers give us something odd and the other one something even?
Because there is a certain number that will be multiplied by itself. It will not be paired up to any other numbers to get the 36. So for 36, it will be 6.
Actually, I'm gonna play a trick with you just so that we get done faster. If you divide 30 by 1, what do you get?
30.
If you divide 30 by 2, what do you get?
15.
If you divide 30 by 3,
It'll be
10.
10.
10.
and 5 times 6,
30.
so can you see how we match them up?
Yeah.
Yes.
How do I match up 46? 6 goes together with whom?
8.
8.
And 4 goes with?
12.
12.
And 3 goes with?
2 with
16.
24.
Get it?
2 with 24.
So we
Nice.
get perfect pairs, 1 with 48, 2 with 24. Now let's do the same thing with these ones in here. So 1 goes with?
36.
36.
Who's gonna be the troublemaker there? 4 goes with?
Number 6 will be the troublemaker. 4 with 9. 6 with 6.
Yeah. 6 doesn't have a partner.
Mm-hmm. Oh, yeah.
6 and 9 is 54.
Then 3 and 12.
Get it? So 3 goes with 12, and 2 goes with
2 is
18.
18.
Good? But remember, these ones were students. So basically, these guys are holding hands, and these girls are holding hands, and whatever. I don't care who's holding hands with whom, but they are always in pairs. Good. So number 2 switches things around, and then number 18 undoes what number 2 has done. Is that a good way of looking at it? Student 3 flips it, and student 12 flips it back. So what I'm doing is I'm pairing up the students who undo each other. And at the very end of the day, who is left? nobody undoes what number 6 did.
Mhm.
Good. And so if we don't have a square number where we have somebody has to undo herself or himself, whatever they have done, everyone has a partner who undoes whatever they did a moment before. Then we get an even number, and so all the other numbers are off. Good.
Yes.
Are you with me?
Yep.
So what matters is how many divisors each of the light bulbs has. So 48 has an even number of divisors, 36 has an odd number of divisors, and 30 has an even number of divisors. Good? So this one, I think, is the classical problem, which was in some math competition long ago, and now it's all over the internet. What I wrote down in here on the top is the number of switches. So can you see the red numbers here on the top?
Yes.
Good. So this one is 1, 2, 2, 3, 2, 4, 2, 4, 3, 4, 2, 4, 6, 4, 4. What we calculated was that, weeks. There's something wrong in there.
1, 2, 2.
Oh no.
One, 2, 2, 3, 2, 4.
So what I wanted to have is that we have an odd number of switches. So I'm counting how many times it gets switched, and the odd ones are at 1, at 4, at 9, at 16, at 25. That's all good, but then something funny is happening. Oh, sorry. Something funny is happening here, and I don't know why. So my worksheet isn't good. But you understand what I'm doing is what we just did by hand, where we were counting how many divisors each number had. And I wanted to use the spreadsheet to calculate how many times it's turned off and on. And then we have even and odd numbers, and apparently somewhere is a mistake in there.
Yeah, starting from 29, I think.
I don't know the formula. So I want to just show you what I have on the spreadsheet. So I will share this one with you. So on the top, I just have the numbers 1 through 100, and then 1 through 100 on the bottom. And this one was a counting function, and that one uses something which is on the side. And apparently there's a Oh, I see what the mistake is. This one isn't filled down. Let's not. Yeah.
96 to 100.
Oh, what happened?
Maybe you switch to other tabs. Yeah.
Let's see. This one is where I want it to be. On the top. Does it look better now? 36 is 9. Where's the next odd number? After 9?
That is 36, 49.
49. That one looks good. And all the other ones are even. Agree?
64, yeah.
Good. So what I did in this green and pinkish region is I'm just counting how many times it flipped. And I don't know how to do this one better in Excel, the counting, but have a second table on the side, which just compares each number. Is it the same as the one above, or is it not? And so that one then uses some numbers. If you look here, FT, can you see FT?
FT4 colon FT1.
Good. So what we have is we have A, B, C, D, and then we get A, B, A, C, and then we get B, A, B, 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 C. So you see this one is far to the right somewhere. Good. So that's just some tiny number on the side. So don't worry about these ones. It's just some complicated way of counting the number of switches. But I want to show you just what is in the spreadsheet in here. And I have one formula in here. And I hope that this one is actually understandable. So I have copied the same formula all the way around. And let me start with the one on the top line in here. So this one is the cell U4. Okay? Oh, sorry, U4. Yeah. So this one is mod. Have you seen the function mod?
Is it module?
So 13 mod 3. Can somebody, oh, sorry. Can somebody, who has seen this one before?
I've encountered that in our college days, but I forgot.
So is
13
that the
module.
one where we care about the remainder?
So what we do is we have 13 is equal to 4 times 3 plus 1.
Okay.
So we're dividing by that number, and mod just tells us what the remainder is. Good. So everybody who is doing even elementary school is doing this one all the time, where you divide and then you just look at the remainder. Is that fair?
Yep.
Good. And so what I have in here is I want to divide the door which I am in. So it's 3 divided by 2. What is the remainder when 3 divided by 2?
1.
1. And when I have 8 divided by 4?
0.
0. So I'm just calculating if there is a remainder or there is not a remainder. And so what I'm doing is I'm checking if a number is divisible, and we have that 8, door number 8, so that is this one in here. Door number 8, will that be turned over by student number 4? Will student number 4 do something to the 8th light switch?
Yeah.
Yeah, so this one switches. You can see it goes from on to off. Agree?
Yep.
And I switch this one only when the remainder is equal to 0. Good. So what my calculation is, I calculate V1. So this one is, where am I on? I want to be all the way in the corner. So I'm always looking at what is in the S column. So the S column is the door number. This one is the student number, and this one is the light switch. So I'm counting off light switch 17 divided by student number 3. If the remainder is 0, what I'm gonna do is I'm gonna make zeros into ones and ones into zeros. So this one is a simple way of saying, if it is a 1, make it into a 0, and if it's a 0, make it into a 1. So 1 minus 1 or 1 minus 0 just switches this one around, and otherwise we just keep it the same way. So this one is not a monster formula, it's just a reason what computer geeks do all the time. So, and now what I'm doing is I take that formula and copy this one. So I don't like my spreadsheet in here. Undo. So I take this formula and then I just copy this one all the way down. So it is Control D, Control R. Once more. I take a formula and then I copy this formula down and to the right, and it just copies this one all over. Only what it does, it says it's always the number on the top and the number on the left. Agree? So it's not that hard. And then I color the whole spreadsheet in here, and I just say that we are doing home, conditional formatting, color scales. Good. So I make the zeros one color and the ones the other color. So I made it black and white here. Good. But I could have chosen them to be yellow and blue just as well. Good. So there is not much magic behind this one. Okay, so this one is when every student walks. So let's do some of the other ones. So when every student walks, then at the end of the day, only the square numbers are on and all the other numbers are off. So let's go back to this one in here. So Josh has a whole other idea of walking. So let's take, for example, that only the let's see, which one was the easier one? Yeah. Let's take that only the even students walk. And for me, the best way of doing this one is restart this one again from scratch. Don't save. That was not correctly planned for me, but light bulbs, right, left, down, right. And the way I set this one up to make it a little bit easier. So computer technology is hard. So here on the side, I made some lists in the front. So these ones are the students who are walking down the hallway. So what we had is if every student walks down the hallway, then something happens down here to the right, okay? And now we're gonna change this one and say, I'm only taking the even numbered students getting some exercise. Okay, so I select the even numbered students and I tell them to walk down the hallway. So the first one is missing. So the second student, what does the second student do? It turns
Then turns up.
on, and then
And
what do
then
we get after this
stay
pattern?
off. Keep change.
Good. What's the next student gonna do? So the next student is number 4.
Number 4. Keep.
What does that one do? It changes. Which one is the first one it changes?
The first. That's third one.
The fourth one.
The fourth one.
And what's the next one which gets changed?
8.
So what's the pattern gonna look like?
Every after 4s. So keep change.
Oh, control down. Does that make sense?
Yeah.
So once more, the second student turns on every other light, and then the student number 4 turns off all the ones which are multiples of 4. So 4, 8, 12, and 16, they all get dark. Okay?
Yeah.
What does student number 6 do?
Change it on the 6th, on the factors of 6.
Agree? And what's the next one which gets changed?
At 12, at 18.
It's on. Agree?
Yeah.
Good. So if we keep going this one, that only the even students walk, what do you expect to happen?
Only the perfect square are turned off at the last day, at the end of the day.
Let's oh, this is beautiful. Now, somebody else, please add something to this one.
What happened? Oh, it's different.
So which is the first one which stays on?
At the end of it's 8.
It is number
8.
8. What's the
Yeah.
next one which stays on?
18.
18. Compared to what we have done before, what was the last time what we had? We had 1, 4, and 9 stayed
9.
on.
The perfect squares.
And now it is 8, 18. What's probably the next one?
18. There are 30,
36.
32, and 34.
Oh, dang
I can't figure out.
it. Do I have a mistake in here?
I can't figure out.
Oh, there's something not copied correctly. Yes, I had something. Can you see here on the right top? I did not copy my formula all the way. I'm managing my screen. So what happens? Which ones are the ones which are on at the end of the day?
8, 18, 32.
Actually, there's one at the beginning.
Yeah.
Which one is this?
2,
2,
8,
8,
18, 32, and 50. To the power of 1.
Does that make sense? What are those numbers?
They are even, but
But they are more than just even. How are they related to the previous ones?
they are. No.
What was, yeah, so if they are even, let's divide them by 2. What do we get if we divide 2 by 2? We get
1.
1. Here we get 8 divided by 2 is
3.
what?
Sorry,
8 divided,
4. Sorry.
18 divided by 2.
Is
9.
9. Oh, yeah. That is divided 3, 16. 32
Once more,
divided
1,
3,
4,
16.
9.
16. 25.
Get it?
Perfect squares multiplied by 2?
Yeah, we got it. We got it. Can you explain why this one is? Nothing ever happens to the odd number door lights, agree? So if I was to remove all the odd lamps and I just have the even lamps left, and then I renumber all of these ones and say this is lamp 1, this is lamp 2, this is lamp 3, this is lamp 4, then we really are back to the old problem. Good? Okay, let's change this one to that only the odd students walk. Let's see if I can do this one quickly. So if I take my odd numbered students, oh, this was bad. Just a second. I have to paste by value. Let's think about what's the first odd student? It is number 1, and it takes all the off lights and turns them all on. Agree? So we have a first white row. Which ones are turned off? The next student is number 3, and number 3 turns off light 3, light 6, light 9, light 12, and so on. Agree? Student number 5 changes light 5, light 10, light 15, and so on. Which ones are left over at the end of the day?
The perfect square and the perfect square divided by 2, times 2.
Once more, let's read these numbers. So 1 and 2, 4, 8, 9, 16, 18, 25, 32, 36. What are these numbers?
The perfect square and the perfect square times 2.
Once more, so perfect squares 1 and 4 and 9
And
and 18.
16.
No, sorry, 16, 25, 36, and 50. Good. And then the other ones, which are not perfect squares, are the numbers 8, which is 2 times 4, 2 times 1, 2 times 9, 2 times 16, 2 times 25. Get it?
Yes.
Good. I don't want to continue this forever. Let's do one which is, so this one is, so there's always good explanations why this one happens. And just as before, we look at the number of divisors, and the door is, the light is on if the number of divisors is, if the number of students who have numbers which are divisors of, that one is too hard to say. Good, so we are looking at a small number of students, so every third student going through. One of the more fun ones is, let's do this one in here, going strictly down the line. It's only the prime numbers walk. So if only the prime numbers walk, and all other students can take a break. So these ones are the first 100 prime numbers, and it's in here. So I paste in the prime numbers in here. Wow, that's a mess. Can you explain what is going on? Let's take 30. That's an interesting number, I think. So who switches 30? And I'm going to move this one a little bit to the right, make this one smaller. I need more space in here. So I have light number 30 and I have the prime numbers walking by. Who switches number 30? What's the first prime number? The first prime number is 2. Does 2 turn 30 over?
Yes.
2 turns on the second light, the fourth light, the sixth light, the eighth light, the 10th light, all the even numbers. Is 30 an even number?
Yeah.
Then the third one walks through and it switches number 3, it switches number 6, it switches number 9. Does it switch number 30?
Yes.
Who else is gonna switch 30?
Number
Is 5 switching 30?
6.
5. No.
Yes.
Ow, please don't run away here. So student number 5, is student number 5 switching the light
Yes.
number 30?
Yes.
Yes. Anybody else? Does 7 switch 30?
No.
11?
No.
13? No, we only
No.
test for primary for divisibility up to the square root of 30 basically, so there is none in there. So why is 30 on at the end of the day? Because 30 is equal to, no, yeah, 2 times 3 times 5. How many times does it get switched?
3.
Yeah. So student number 2, student number 3, and student number 5 switches it. Agree? So a while ago, I had the same 30, but at that time, when all the students were walking, good, when all the students are walking, we are looking at all the numbers which are dividing 30, and we had, for 30, we had, how many were these? 8 divisors, and that was an even number. Agree? But now we are not looking at all divisors, but we are only looking at the prime divisors, prime numbers which are divide 30 evenly. Agree? So pick another number, 24. Is 24 off or on at the end? Who is gonna change 24? Student 1? No, 1 is not a prime number. Student 2? Does student 2 do something to it?
3 and 3.
Yeah, so 2 turns it on and 3 turns it off. And then, are there any other prime numbers divisible into 24?
No.
Good, so 24 is 2 times 2, it's 4, times 2 is 8, times 3. So 24 is equal to 2 times 2 times 2 times 3, but this one only contains 2 prime divisors, and that means that there's only 2 students who turn this one on and off, and that's it. Get the idea? 21, is it on or off at the end of the day? Can you factor 21?
Yes.
7 and 3.
3. Yeah.
3, so 3 turns it on and 7 turns it off. Good. Let's take a more complicated number, 27. What is 27 if we factor that into primes?
3 and 3 and 3.
3 and 3 and 3. How many different prime numbers are those?
1.
1. So 3 turns it on and then nobody else turns it off again. Agree? So student number
Yes.
3 turns it on, and it stays on. What happens to 10?
2 and 5.
Yeah, so 2 turns it on and 5
Turns it off.
turns it off. Good. Let's take a number which is a little bit larger. What happens with 48?
6 and 8.
They are not prime numbers. What are all the different prime numbers in 48?
2 and 3.
Yeah, it's 2 times 2 times 2 times 2, a whole bunch of 2's times 3. So 2 turns it on and 3 turns it off. 54.
54 is.
It's an even number. Agree? So
So
2
2
turns
and
it on
3.
and
2 and
3
3
turns it off.
turn it off.
off. And that's all that is in there, because it is, I think, 9 times 6. So it's a whole bunch of 3's and a 2. What happens to 53?
53 is a prime.
53 is a prime number, so it stays dark all the way until we get to, oh, there it is, 53. And that one switches it around. Good. So what we do for, if the prime numbers are the ones which are walking, we take our number, write it as a product of primes, and then count how many different prime numbers we have in that expansion when we factor it. And then we just count how many different ones, and then it matters if it's an even number, an odd number. Take a look at these ones are all 1 or 2, 1 or 2, 1 or 2 switches. Where's the next 3? So where was the first 3? 3. This one was 30, was 2 times 3 times 5. What is 42? That is
2 times 3 times.
yeah, 2 times 3 times 7. Where's the next 3 in here? Oh, there's a pretty one. 66 is?
Oh, 2, 3, 11.
Good. So it's 3 different prime numbers in there. Good. And so as we go further, it takes a long time until we get 4 different prime numbers. What are the 4 smallest prime numbers in there? It is 2 times 3 times 5 times 7. So if we multiply that out, 2 times 5 is 10, and 3 times 7 is 21. So if the first time that I would get a 4 in there is when we are at the 210th light bulb. Again, 210 is 2 times 3 times 5 times 7, and I don't even have that many light bulbs on my sheet. So we only get 1, 2, or 3 different prime factors. Good. How are we doing with time? Dave, are you still on there?
I am. I need to. I'm muted. Oh, am I muted? I'm not muted. So I think we are pretty good. I mean, you've been with each of the 3 of us have gone a bit over. If you're able to wrap up, I think people would be happy with that.
So I would like to oh, what happened there? I hate this. I don't do starts. I don't do Microsoft. Get out of my way. Good. And I want this one all the way. I'm gonna make this one larger. And good. So what we have been playing is the one which is of the math competition problems, AMT problems, which is on the web everywhere, is that everybody walks in and turns the first, the second, and so on over. And at the end, we're just left with the perfect squares, 2 times the perfect squares. This one is both of these ones together. It's kind of surprising. We have worked the primes. We can also make all the perfect squares walk, all the multiples of 3, and so on. And the original idea was that we can work this one on paper just by crossing things out. Good. So this one is what I did at the beginning. And you can use either an eraser or you get just more paper in there. But this one should be feasible with students at pretty much all ages. And I said the tricky part was when I'm coloring. I'm coloring when I make a change. No. I'm counting off when to make a change, but I have to color according to what was there before. And so I made plenty of mistakes in there, but I think this one is doable, and working this one with coins is even easier. So you don't need many rows under each other. You're actually flipping the coins. Tail, heads, tail, heads, tail, heads, and then you flip every third one. So you really can do this one in a hands-on way. And the idea then beyond the traditional problem where everybody walks, we only have certain kinds of people walk, and there's all sorts of interesting groups of students that we can take. And yeah, this one is what we worked at the very end. Given any set of people, we have a general strategy for figuring out what works, because we look at the divisors and then match up the divisors with what happens. Now comes the fun part. So this one is the back side, and I really like inverse questions. So I'm not working in control theory. I work in control theory, and that one is different from differential equations and dynamical systems. So calculus was invented because the church wanted to make a calendar all the way into the future and find out when Easter is. So they had to compute how the moon goes around the earth and the earth goes around the sun, and when you have equinox and you have a full moon, and there was a rule for Easter. And that one is kind of boring for me, because that just says what will happen, what will happen, what will happen. What I like to do is, I don't like the planets that much. I like the space shuttle and rockets much more. And so I have the same laws, but I want to get to the moon. So the question is, how do I get there? How do I get to something? So now the goal is, I'm not telling you which students walk and then what the result is. So once more, each of these ones said, what happens if, what happens if, what happens if these students walk? All the way through math, the inverse question is often much more fun. I ask, which students should walk so that all the bulbs are on? Which students should walk so that only the even bulbs are on? Which students should walk so that the perfect squares are the only ones on? Who should walk such that only the perfect squares are on? Do you remember?
Everyone.
Everyone walks, good. But this one is a very different question where we just say everyone now is the answer. Good, so this one is now the answer, and this one is the problem. So we are turning this one around. If we want to have that all the bulbs are on, who should walk? At the beginning, all of them are off. Who should walk and turn all of them on?
Student.
Which one? How many students?
Student number 1.
Yeah. Student number 1 turns all of them off, and we're done with the problem. Get it? Who should make sure that only the even ones are on? Oh, let's do it the other one first. They are in order. You know, math problems, teachers always put them in order that you use the previous answer for the next one. If we only want to have the odd ones on, how do we get the odd ones on? Either one of them.
They turn on when the students with even number, the even number students walk.
Yeah, remember when students 2 and 4 walk and so on, they get pretty fancy patterns. So if all the even students worked, remember the even ones, they gave us the numbers 2, 8, 18, 50, and so on. This ones were 2 times 1, 2 times 4, 2 times 9. Oh, sorry, 32, 50. So this one is 2 times 16, 2 times 25. So this one is if all the even students work. But if we own, so they turn them on and off and on and off, crazy mess. But if we want to have that all the even ones are turned on, who can turn the even ones on? Which student is good for the evens?
I think even numbers. 2, 4, 6. 1, 4, 2, 4, 8. 2, 4, 8.
So what happens if only student 2 walks through? What does student 2 do? It turns on which lamps?
Turn on the perfect square times 2.
No. If only student number 2 walks, which lamps are turned on after student number 2 walks?
All the even.
All the even numbers.
So this one is done. Agree? Only student 2 walks. How do we get all the odds ones on?
By odd numbers.
If student number 3 walks, then we get 3 and 6 and 9 and 12. No, that is not all the odd numbers.
Oh yeah.
How are the evens and the odds related?
6.
Oh,
Let me do this one no.
odd ones.
So one of them is,
Start with number 1 and then skip all the even. So it'd be 1, 3. No, that won't work.
actually, let's do this one in here. I only have to rearrange my. I don't want to see this one. Let's erase all of them. So what does if only student number 2 walks? Oh, I erased too much. Oh, here. So if only student number 2 walks, oh,
Hello?
I hit the shift button by accident. Oh, I'm at 100,000 rows down. Oh, damn. I think shift arrow gets me up. No, control arrow. So if student number 2 walks, what do we have? The only ones who are on are 2, 4, 6, 8, 10. Agree? And we want to have everything switched. How can we make that everything is switched? Who switches everything?
One.
Yeah, good. So if I have student number 2 walk and student number 1 walk, then which ones are left over at the end? So if student 2 turns on all the even ones and then student 1 flips all of them, then the even ones are turned off and the odd ones are
On.
turned on. And I just discovered something which I hadn't seen before. Does it matter who walks first, 2 or 1? Do we get the same result?
I believe it matters which one walks first.
Think about it. Does it matter in which order we walk?
No, because they're opposites.
Actually, let's discuss this one a little bit. What matters at the end of the day? What matters at the end of the day is how many times it is turned on and off and turned on and off, and we want to count, is it an even number or an odd number of times that we turn it on and off? Agree? How many times is it turned on and how many times is it turned off? It doesn't matter who goes first. Are you with me? So if I look at light bulb 48, and now they go in the order 6, 8, 4, 12, 3, 16, 2, 24, 1, 48, then they always go in pairs, and I turn it on, you turn it off, I turn it on, you turn it off, I turn it on. But it doesn't matter who goes in there, it just matters if it's an even or odd number. Agree?
Yes.
Good. So that is something, thank you. You taught me something when I had these ones in the wrong order. I just learned that it doesn't matter in which order we put them, we still get the same result. Okay? So what I think is, what I'm gonna do is, I wanna leave it with this one. I'm gonna make this sheet, I'm gonna make this sheet available to you. So this one should be on the website.
On the website now, yeah.
And then we already had a template like this one out. I have the gray lines in here to make it a little bit easier. So they are the 10s, 20, 30, 40, and the lighter gray is 5, 15. But I did not manage to do it in both ways. And every time that I fill down, it changes the color again. So that one did not work as well. And then the worksheet, which I'm using here, is I'm gonna share this one, and you see that I wasn't perfect with that. It takes a little bit longer, but now it takes, what do we have for the primes? 2, 3, 5, 7. So it's pretty easy to say which students are walking and then see how it switches. So this one works, and for the purposes of this session in here, I just made these numbers here on the side so I can copy and paste them in here. So these ones are I'm sorry, when I did this copying, what I have is I have a formula in here, and I copied the formula, but what I wanted to do is I didn't want to copy the formula, but I want to just copy the numbers. And to copy the numbers, I just say copy the values. Good. And now we have the 3, 6, 9, 12, 15 walk, and these ones are the results. Actually, let's finish with this note in here. This one is actually a nice one to come out. Which rows are left on? If only the students 3, 6, 9, 12, 15 walk, take a look what's left over at the end. It is 3. Who's the next one which is on? 12, 27. What are those numbers? Remember, we have a 3 in here. So it's 3, 12, 27. They all have a 3 in them. Agree? What happens if you take the 3 out? What's the next number in this list? 3, 12, 27, 48. What are those numbers? Let's take a 3 out. What is 3 divided by 3? 1. What's 12 divided by 3?
4,
What's 27 divided by 3?
9.
What's 48 divided by 3?
So it is the perfect square divided by 3. Or
16.
perfect square times 3.
16. What's the next slide which is on? Oh, I didn't copy this one far enough.